In this video, we're going to talk about when metric spaces are topologically equivalent. So here's our definition. Two metric spaces, xd and yd prime, are homeomorphic or topologically equivalent if there's a bijective function f that maps x to y such that both f and f inverse are continuous. And in this case, that function f is called a homeomorphism. Just a reminder, because f is a bijection, that means it's one-to-one, and so that means f inverse exists. And for this to be the case that both f and f inverse are continuous, let's just remind ourselves the definition of continuity. So we have the definition of continuity in a metric space, this epsilon delta definition of continuity. For any epsilon greater than 0, there is a delta greater than 0, such that the distance between a point x and a point A being less than delta in x implies that the distance between f of x and f of A is less than this epsilon in y. Or we could also use the alternative definition of continuity. We showed that this is logically equivalent previously by a theorem, that a function f mapping x to y is continuous if and only if for any open set u in y, f inverse of u is open in x. And so because f inverse is also continuous, note that f inverse is just f again. So if it is the case that f is a homeomorphism, then it's the case that for any open set, say v in x, then f inverse f of v is open in y. Being homeomorphic or topologically equivalent is an equivalence relation on metric spaces. As a reminder, an equivalence relation is a relation that's reflexive, symmetric, and transitive. So reflexive means that any object is related to itself under the relation. Here that would mean that any metric space is homeomorphic to itself. Let's think about why that's true. A space is homeomorphic to another space if there is some bijective function, f mapping one space to the other, such that it and its inverse are both continuous. So can we think of some homeomorphism here, f mapping xd to itself that is continuous? So does there exist some function f mapping xd to itself that is continuous, where f inverse is continuous as well? Yes. The most obvious example would be the identity function. So let's let f be the identity function. In other words, f of x is just x. Then if we've got an open set over here, then its inverse is just itself. It's in the same metric space, so it will be open over there. If we've got an open set over here, then its inverse will be open over there. The inverse will just be the set itself. If it's continuous in xd, it's continuous in x. If it's open in xd, it's open in xd. Therefore, the identity function is continuous. And therefore, any metric space is homeomorphic to itself. So the equivalence, so the relation homeomorphic to satisfies the reflexive property. How about symmetric? So for symmetric, we're assuming that xd is homeomorphic to yd prime. So xd homeomorphic to yd prime implies there exists some f mapping x to y that is both bijective and continuous, and f inverse is continuous. That's again our definition of homeomorphism. And so therefore we immediately have that because f is bijective, that means that f inverse is bijective and then also continuous by definition. And again, f inverse is just f, which we already know to be continuous. And lastly, transitive. we want to show that if xd is homeomorphic to yd prime and yd prime is homeomorphic to zd double prime, then xd is homeomorphic to zd double prime. So this we can just immediately show by composition of functions. So because xd is homeomorphic to yd, there exists f, a homeomorphism mapping x to y, and because yd prime is homeomorphic to zd double prime, there exists a g mapping y to z that is a homeomorphism. Now, the composition of functions f composed with g is then going to be a homeomorphism mapping x to z. We already proved that if f and g bijective implies that f composed with g is bijective, and you'll be showing in the homework that if f and g are continuous, this tells us that f composed with g is continuous as well, and therefore the composition of the inverses will also be continuous. Because is homeomorphic to is an equivalence relation, that means that this relation partitions the set of all metric spaces into disjoint sets. So we've got these disjoint sets of metric spaces x comma d, y comma d prime, etc., or d whatever, and z d. All of those must be homeomorphic to one another, and some other set of metric spaces, a star, blah, 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 and all of these are homeomorphic to one another, and so on. So these are disjoint sets, and every metric space falls into exactly one of those sets. Every metric space in that set is homeomorphic to every other one in the set and to no others outside of that set. So let's look at an example. Let's let a and b be real numbers where a is less than b. Then the open intervals 0, 1 and a, b with the usual metric are going to be homeomorphic. So we've got 0, 1, the open interval, and ab, whatever ab is, ab, and this is going to be homeomorphic. To show that they're homeomorphic, we need to find a homeomorphism between them. So for this, we can just find a linear function. So if we want f of 0 to be a and f of 1 to be b, then we can make this a linear function where our slope m is change in y over a change in x. So that's b minus a over 1 minus 0. That's b minus a is our slope. And then we would have f of x is change in b minus a times x plus our y-intercept. We know that our y-intercept is f of 0, and f of 0 is a, so our y-intercept is a. And then that means that this is a linear function. This is a linear function, f mapping the open set 0, 1 to the open set a, b. And as you will show in the homework, linear functions mapping r to r with the usual metric are continuous. And because they are continuous, so that function is continuous, the inverse of a linear function is linear as well. So that means that that is continuous also. And therefore, this is a homeomorphism. So f is a homeomorphism mapping the open interval 0, 1 to the open interval ab, and therefore these two sets are homeomorphic. As another example, in the real numbers with the usual metric, the function g of x equals tangent of x is a function, and it is 1 to 1 if we're just looking at the interval from negative pi over 2 to pi over 2. It passes the horizontal line test, and it maps that interval to the whole set of real numbers from negative infinity to infinity. We know that this is continuous and that its inverse is continuous as well. And therefore that means that the interval from pi over 2 to pi over 2 and the whole set of real numbers, or is homeomorphic to the entire set of real numbers, if we're talking about, again, the usual metric. So this tells us that the real numbers is homeomorphic to, we could do that, is homeomorphic to the set negative pi over 2 to pi over 2, which is also homeomorphic to our set 0, 1, that interval by above, and any open interval from A to B will be homeomorphic. So all of these are in one equivalence class of homeomorphic metric spaces with the usual metric. As one more example, let's look at D with let's let D be the usual metric and capital D be the discrete metric. Then the real numbers with the usual metric and the real numbers with the discrete metric are not homeomorphic. So one way we could show that these are not homeomorphic spaces is to show that there can be no continuous function. So not homeomorphic means there is no bijection F mapping the real numbers with the discrete metric to the real numbers with the real numbers with the usual metric to the real numbers with the discrete metric, such that F and F inverse are continuous. So showing that something is homeomorphic, that two spaces are homeomorphic, means there is some bijection with these properties. Showing that two spaces are not homeomorphic means showing that there is no such function. So let's see if we can show that. Let's let F mapping R with the usual to R with the discrete be any bijection. So what do we know about the discrete metric? We know that the distance between 2 points x and y is 0 if x equals y, 1 if x is not equal to y, and therefore we know that the ball centered at any value y of radius, any radius less than 1 but greater than 0, radius 1/2, say, is equal to only the point y. So the only thing of distance less than 1/2 from a point is the point itself. We know that an open ball is always an open set, and so this is open in R with the discrete metric. However, F inverse of this open set, this set containing just y, that would be, F inverse of y, whatever that is. This is a bijective function. This is 1-to-1 and onto. So there is exactly one such element, F inverse of y. F inverse of y is an element of the real numbers with the usual metric. And this set containing just one element, F inverse of y, is not open in R with the usual metric. How do we know that that's the case? Well, we know that if we think about, again, the ball centered at this point, F inverse of y, with radius epsilon, where epsilon is greater than 0, then there's going to be x element of this ball, x an element of this ball centered at F inverse of y of radius epsilon, such that x is not an element of the set containing just that one single point, F inverse of y. So while the set containing just y is open in the real numbers with the discrete metric, it is not open in the real numbers with the usual metric. So F inverse of y is not open in the real numbers with the usual metric. Despite that, F that this set containing just y is open in the real numbers with the discrete metric. And therefore, by one equivalent definition of continuity, we know that a function is continuous if and only if, for any open set in the range, for any open set in y, its inverse is open in x. So therefore, f is not continuous. And the only requirement we had was that f was a bijection. So no bijection can be continuous, mapping the real numbers with the discrete metric, so with the real numbers with the usual metric to the real numbers with the discrete metric. And therefore, there is no homeomorphism f mapping the real numbers with the usual to the real numbers with the discrete. And so these spaces are not homeomorphic. Here's a theorem talking about when x with one metric is homeomorphic to x with a different metric. So let d and d prime be two metrics for the set x. Suppose that there are positive numbers c and k such that the distance between x and y is always less than or equal to c times d prime between x and y, and d prime between x and y is less than or equal to k times the distance between x and y for all x, y, and x. Then the identity function is a homeomorphism between xd and xd prime. So we've got x and we've got a copy of x over here, but one of these has one metric and another has a different metric. So kind of like what we saw above with the real numbers with the usual and the real numbers with the discrete. Here we're thinking about when will they be homeomorphic. So we're looking at the identity function now, and the identity function is that has just any element maps to itself, and its inverse, I inverse, is just the function I. So x maps to itself and the inverse maps x back to itself. And so what we want to show for any epsilon greater than 0, there is a delta greater than 0 such that the distance between x and y being less than delta implies that the distance between distance d prime between I of x and I of y is less than epsilon. That would tell us that f is continuous, or that I is continuous. Okay, so what do we know? One thing we know that is that d prime is less than or equal to k times the distance between x and y for any x and y and x. So let's let epsilon be greater than 0, and let's let delta be epsilon over k. Then, if the distance between x and y is less than epsilon over k, that tells us that d prime between I of x and I of y, that's just d prime distance in this metric between identity function on x is x, identity function on y is y, and that is going to be less than or equal to, according to this, k times the distance we had, epsilon over k, which is epsilon. So we do have that I is continuous. Similarly, I inverse equals I is continuous. Now we'd just be using this instead. And it's clear that I is bijective for every one element over here. We have exactly one element over here and vice versa. So I is a homeomorphism. The identity function is a homeomorphism. If x with the metrics d and x with the metric d prime are homeomorphic, then we say that d and d prime determine the same topology on x, or that they are equivalent metrics. As an example, I'd like you to take a look at in our book at the end of this section is that the usual metric and the taxicab metric are equivalent metrics on the set of real numbers. So we saw above that the discrete metric is not an equivalent metric to the usual metric on the set of real numbers, but this is telling us that the taxicab metric and the usual are. So if we just think about, open balls in the taxicab, this is for r squared, and open balls in the usual metric, then, we see, first of all, that this ball in the taxicab metric contains the ball in the usual metric. So if we have 2 points, x and y, that are of distance less than 1 from each other in the usual metric, then they are also of distance less than 1 from each other in the taxicab metric. But we could figure out some, if we did the ball centered at 0 of radius 1/2 in the taxicab metric, then that would be a little square that's inscribed in this circle, right? And so our book describes this a little bit more precisely. But that would be a situation where if d prime is taxicab, then the distance d prime between x and y in the taxicab is always going to be less than or equal to the distance between x and y in the real metric times 2.